equals symbol number 1. Grams nope. Am I solving for the grams of sulfur? It is a molecule, and this is where visual design has bitten us. Is sulfur just a molecule? No, what is sulfur? An atom. If it says molecule, it's not sulfur, it's sulfur dioxide, which means it's SO2. Okay? So the visual design of that statement, you went through and said grams, awesome, and then said molecule sulfur. Within that line, it does have that context, but we have to remember that the line can continue. Molecule can't possibly tie to just sulfur. It has to tie to sulfur dioxide. So the question split across lines. Okay, while that is unfortunate, we have to watch out for that. That's the English language. Okay? What are we given?
64.07 grams per 1 molecule.
Okay. So we could go through and say we are given 64.07 grams of sulfur dioxide. And that's not true. What are we given? Grams per mole of sulfur dioxide. And in particular, 1 mole of it. We're also given something else. The molar mass is 64.07 grams per mole. Nope. What are we trying to find the mass of? What else are we given? We are given 1 molecule, that says molecule, of sulfur dioxide. Okay? We now need to take that given information and somehow arrange it into our expression. Okay? Because we were given a glut of information, we could change how we go through and start. So, how do you guys want to start this solve? So we'll look at 2 methods to do this. We'll look at the middle one, and then we'll look at a top one. What do you want to start with? Okay, so I have a suggestion for moles to molecules. Where are we trying to end? Grams. Our moles, grams. No, our molecules, grams. Why would you start with moles to molecules? And I'm not saying you're wrong, but why? Why are you starting with moles to molecules?
Because the end goal is to get the mass of 1 molecule.
The end goal is to get the mass of sulfur dioxide. That's the end goal. Grams of sulfur dioxide. That's it. So by saying the end goal is to get the mass of sulfur dioxide for 1 molecule was given to you. You were told 1 molecule. So you aren't being asked to solve for 1 molecule. You're being asked to solve for grams of sulfur dioxide. So you may very well use molecules and moles, and I'm not saying that's wrong, but why are you using that? You're being asked to solve for grams, and you're suggesting a conversion factor that has nothing to do with the unit of grams. So one suggestion, you're given the unit of grams in the given information. Grams of sulfur dioxide. What do we want for an answer? Grams of sulfur dioxide. So where should that grams of sulfur dioxide from our given information show up? It should show up in the numerator, on top of a fraction. So we could go through and say grams of sulfur dioxide. That is related to moles of sulfur dioxide. The numerical relationship is 64.07 and 1. Okay? That is a valid place to start. Okay? The problem with that is typically the molar mass is not given to you. You're expected to solve for it. Okay, so that becomes a challenging one to start with because you're being given kind of a softball here. You're given that extra information. You may have to find that otherwise. Okay, so what if we weren't given that information? What could we start with?
I give the molar, atomic mass.
So we can go through and find the atomic mass. So you're saying I want grams. I know I could get a gram value from the periodic table. I could find the molar mass. Okay, which again doesn't put anything into our expression.
Well, you want to get rid of one mole.
What things are you given? How many things are you given? Two things, 1 and 2. You all identified 1. If we get rid of that and say that's not given, what else is given?
One molecule of SO2.
What do you think we should start with? 1 molecule of SO2. That is another way that we could start this question. Given 1 molecule of SO2. Okay? We're trying to come up with why are we starting with what we're starting with. If you know why you're using it, you now have an approach, you have a process. If you don't know why you're using it, you could very easily place the units in the wrong space. Okay? So again, focus on the why. Why would I place 1 molecule of SO2 in the numerator and not in the denominator? What about where I'm aiming for would suggest molecules of SO2 should show up in the numerator?
SO2 is the answer.
The substance I'm solving for is sulfur dioxide. Where does it show up in the answer? In the numerator. Where should it show up in my work? In the numerator. Okay? Given that it's a single system, not a conversion factor. Make sense? Okay, which one do you want to look at first? The top one or the middle one?
Middle.
Okay, I heard the top first, so we'll bounce back and forth. And the top one, is a molecule of sulfur dioxide the same thing as grams of sulfur dioxide? No, so what do you have to do?
Cancel out molecule.
Molecules of sulfur dioxide must disappear. I'm not writing molecule ever, well, I'll probably write it sometime again. But MLC is my abbreviation. Sulfur dioxide. What do I want to convert it to?
Grams.
Grams of sulfur dioxide. Does that conversion factor exist? Okay. The periodic table does give me mass. Okay, a mass value. What are the units on the mass value from the periodic table? AMUs is grams per molecule in AMU. How do you know that?
Is it not?
The letters AMU are not the letters GMLC. It's literally a direct coding of letters. They aren't the same thing, so they're not the same. What else can be found on the periodic table? If not in AMUs, we can find it in. So a suggestion was moles, we'll go with that first. Is moles a mass? No, moles is a count, a number of particles. So moles might be important, but the periodic table does not tell me moles. Okay. There was another suggestion, kind of playing off of moles and saying a molar mass. Ooh, what is a molar mass? What are the units of a molar mass? Grams per mole. Okay. I have grams per molecule. Is that the same thing as grams per mole? No, why not? MOL is not the same thing as MLC. There's a reason why I use MLC as my abbreviation, because the other abbreviation we could possibly have used from molecule might have been MOL or MOLE, and both of those look like mole. They're not moles. Okay, so it may have been a horrible variable term to assign to moles because it looks an awful lot like molecules, and that was a horrible decision on whoever designed the term for moles. Okay, so we can yell at them. They did a bad job. Okay, oh, you. That is mildly frustrating. Hopefully I don't delete it again. Does that conversion factor exist?
No.
No. Okay. This becomes the challenge in this unit. Okay. Before, in the past units, you have to look it up. You either look at the front of the exam or it was one that you were required to memorize. Okay. Now you have to look at it and be like, am I supposed to know that conversion factor? No. Okay. I need to come up with a new conversion factor. Okay. Do I know I need grams of SO2? Yes. Do I know I need molecules of SO2 in the denominator? Yes. Both of those have to appear at some point in my calculation. Okay. Which one do you want to focus on? You want to focus on molecules of SO2. Cool. That means grams of SO2 must disappear. That has to show up at a later calculation. Okay. It does not have to show up right now, but it does need to show up later. So what we could do is say, I know I need to do that calculation. Because I know I need to do it, I'm going to slide it in next door, okay, as a tracking. Okay? And I don't know what shows up in the denominator of the red conversion. I don't know what shows up in the numerator yet for the blue version. What can I convert molecules to? Moles. Okay, there's an interesting suggestion. Can I convert molecules of SO2 into moles of SO2? Is that a valid conversion factor? Yes. What conversion factor is that? One mole is defined as 6.022 times 10 to the 23rd molecules of SO2. That is Avogadro's number. Okay, so that conversion factor we get from our memory. Avogadro number. This is one that we have to memorize. All right? What would that do for us? So focus simple first. What does doing that conversion do for us? It cancels molecules of SO2. What does it not do for us? It introduces a new unit that I don't want in my answer, which means what do I have to do in my next step? I need to find a way to get rid of it. Okay? So to get rid of it, where does that unit have to show up in my next conversion? In the denominator. Because I had conveniently transferred that grams of SO2, because I knew I needed it, I just said, well, I'm going to put it in the next conversion. Okay? It may not have shown up in the next conversion, but it's now there. Is there a conversion factor between grams and moles? Where is that conversion factor found? Okay? There's two answers for this, which was kind of unintentional. Okay? The first kind of iffy statement that Cody was volunteering was like, this sounds a little dangerous because it looks kind of obvious. It's literally written right above it in the question where it says the molar mass for sulfur dioxide is 64.07 grams per mole. Oh, no, that is right. 64.07 grams is 1 mole. How do I know the 64.07 goes in the numerator? What is the 64.07 closest to in the given information? Grams. Where is grams written in my conversion factor? In the numerator, which means 64.07 goes right next to the grams. What happens to my units? The moles of sulfur dioxide cancel, and what are we left with? What unit would I be left with? Grams of sulfur dioxide. What am I trying to solve for? So now what do I need to do? Now I can punch it into the calculator and deal with it. All right. Before we start punching into the calculator, let's go ahead and look at the next one down below, because a suggestion was made. I don't want to start with 1 molecule of sulfur dioxide. I'm going to start with grams of sulfur dioxide because I know I need that in my answer. Okay? If we look at this other way to go through and solve, what is the problem with that? With that given information, What is the issue? Remember, the equal sign is inequality. These things must be equal on both sides. What is the problem with the given information?
You have all of us, that's what I'm talking
I have moles of SO2. Do I have moles of SO2 in my answer? No. So what has to happen? I have to get rid of that. So I would need some kind of conversion factor, where I would put moles of SO2 so that those units could cancel. Yeah? What can I convert moles of SO2 to? Okay. I could convert it to molecules of sulfur dioxide. Couldn't I also convert it into grams of sulfur dioxide? Does that conversion factor exist? Yeah, absolutely. I could totally do that. That's awesome. Let's just do it. Why not? The goal was to keep grams. If I put grams of sulfur dioxide in the denominator, what happens? I canceled it. Okay, is that a rhetorically useful conversion factor? No, that goes counter to the end goal of my thesis. Make sense? So grams of sulfur dioxide, just because I have a conversion factor doesn't mean I should use it. I have to decide, is it actually useful? So a suggestion was made to instead use molecules of sulfur dioxide. Well, why'd you pick molecules of sulfur dioxide? Okay, one option, dude, Mike, we just solved it, and that's what's written right above it. Fair enough. Okay, how many other conversion factors do you know for moles of sulfur dioxide? Like none. There's really two you've got, molar mass and then the definition of a mole. Well, if it's not molar mass, then it's the definition of a mole. Okay? So we can use kind of a process of elimination to help us sort through that. It's 6.022 times 10 to the 23rd molecules was 1 mole of molecules for sulfur dioxide. What happens with our units? The moles of sulfur dioxide cancel. Awesome, but now my answer would be grams of sulfur dioxide per molecule of sulfur dioxide. What did I want for an answer? Just grams of sulfur dioxide. So what has to happen in this next step? Okay. I need that unit, that molecule unit, to disappear. How can I get rid of that molecule unit? What would I need to find? Should it be a conversion? Should I be converting molecules of SO2 into something else?
No,
Why not?
because you don't want anything on the bottom.
I don't want anything on the bottom. How do I know I don't want anything on the bottom?
There's nothing on the bottom.
Look at the answer. The answer does not have anything in the denominator, which means don't put a unit underneath there, put a 1. That would be my ideal circumstance. But that means in the question, I have to be explicitly told how many molecules of sulfur dioxide I'm reacting. Does the question explicitly tell me how many molecules of sulfur dioxide I'm reacting? It says a single molecule. Why is that a bit frustrating and irritating? What does a single mean? 1. We're using alphabetic text to code the numerical or the mathematical language. You have to be able to interpret that alphabetic text to get the numerical relationship. What happens in our calculation? Molecules of SO2 cancel. We're now set to run the calculation. Are those calculations different from each other? No, they're spot on identical. But the process by which we plugged information in differed depending on what we saw and wanted to work with first. Okay? You could easily have gone through, because there was a suggestion, I want to do with molecules and moles. Okay? The problem with starting with molecules and moles is, well, which one should be on top? Should I have moles on top or molecules on top? And you should all be able to tell me right now what the answer is. Moles should be on top. Why?
So they cancel.
I don't accept, so they cancel.
Because I think it's twice.
Why should moles be on top instead of molecules?
Because molecules on the bottom. Just is.
That's a pretty damn good answer, because it is. How would you know moles should be on top and not molecules? It's literally written in our work. You know the answer, so you know it's supposed to be there. If I get rid of all of that work, how would you know to place moles of SO2 on top? Okay, so there's the suggestion. It's one of the conversion factors we know. That's an awesome idea. I like it. I like it. And I'll throw pens. In orange, is that a conversion factor you know? Yes. So what I'm asking is, if you're going to start with the conversion between molecules and moles, how do you know that moles should be on the top and not molecules?
Because if moles is on the bottom, you'd be dividing 1 by that number.
Which isn't relevant. What are you suggesting? Nope, unfortunately not. You will sometimes use the conversion factor in orange. So how do we know the red one was right or the blue one up here was the correct way to write it and not the orange one?
Because you got shot in the dark here. Because you're given grams per mole, and if you were to be given grams over a mole, saying you were given 64.07 moles, then you would use that. But based upon what you were given in the problem, you have to know.
Okay, and so for those of you trying to track what Molly's saying, and this is really, really hard, because what I'm asking you to do is think beyond this. The reason we're using moles and molecules the way we are in this conversion is because of what we're aiming for and what we are given. Okay? And how those two pieces of information relate to each other. That's why we chose grams of SO2. That's why we chose molecules of SO2 to start with, because we had that information to work with. Okay? And we knew we were aiming with grams of SO2. Okay, the bottom one, 64.07 grams of SO2. I know that goes in the numerator because it's in the numerator. Why should I put molecules of SO2 in the numerator? The substance SO2 is in the numerator. Okay? Is the molecules of SO2 a conversion factor? Okay, to be a conversion factor, you have to relate what? One unit to another unit. How many units show up in molecules of SO2? 1. Is that a conversion factor? No. Is grams of SO2 a conversion factor? No. So they are both just strict measurements. The substance is the same. All we're doing is converting the measurement, which means if the measurement shows up in the numerator, where should my measurement show up? Numerator. What's the issue with using the relationship between moles and molecules first?
A mole is not a measurement.
A mole is sort of a measurement. It's a counting. This is all counting. Okay. Why did I use 64.07 grams of SO2 in the numerator? Because it matches the answer. Why did I place molecules of SO2 in the numerator? Okay. It matches the answer that I'm looking for. It's the substance and just a measurement. When I look at the mole to molecule conversion, what's the problem with it? Does it match the format of grams of SO2 in any way, shape, or form?
SO2.
Grams of SO2 is a measurement. Molecules per mole is conversion factor, so it doesn't match the answer. Okay? Does it at least give me grams of SO2? No. Nothing about that conversion factor matches what I want for an answer. Molecules of SO2 is a measurement. That matches my answer because I'm being asked for a measurement. Grams per mole is a conversion factor. That's bad because it doesn't match my answer, but One of the units in that conversion factor matches my answer. There's a reason I can place it there. What is your reason for orange versus red here? Let's get rid of the top one just so we don't have to reference it anymore. What would your reason be? And this is where it sucks. You either put the 6.022 in the numerator and you multiply, or you put it in the denominator and you divide. What is your reason for how you place it? Luck. Pure, unadulterated, blind luck. You took a question that in our both top two methods, we have a logic behind why we're doing something that allows us to move from one step to the next versus orange to red. 50-50 shot in the dark. Let's see what happens. Oh, it worked. Oh, I must know what I'm doing. Unfortunately not. Okay? There has to be a logic behind why you're picking the conversion factors you are. That logic, if you haven't noticed already, goes all the way back to step one every single time we've solved a conversion. There hasn't been a single case where we haven't talked about step one. And what was step one? What do you want? What is your goal? If you do not know what your goal is, you are using blind luck to get through everything, both in this class and in life. Okay? Sometimes luck is awesome. I don't want you to, well, I do kind of want you to be lucky, but not rely on luck to get through life. Okay? You need to have that intent behind why you're putting something in. And if your intent going into the exam is I'm going to rely on luck alone, that's fine. I will accept that. I will get really angry and irritated, not necessarily at you, but that you decided to not listen to anything I've said. Okay? And that frustration comes back to me, because whatever I'm doing isn't convincing you that you shouldn't rely on just luck. Make sense? Hi. Do it again. How many fluorine atoms are present in 2.25 grams of fluorine gas? Set it up. So when we solve it, set up the work, we can figure that out. So this question has some intentional hiccups in it that you have to watch out for. Okay? One of the problems with this question is that two wrongs end up making your answer right, okay, numerically. That is why this type of question would get written in the show your work. You would numerically get the correct answer, but your work would be inherently flawed, and so you would miss a significant amount of points. Okay? So let's track to see where this falls. What are we trying to find?
Atoms of fluorine.
Okay, we are trying to find the atoms of fluorine. Okay, I noticed a couple people going through and writing out atoms of fluorine. That isn't necessarily wrong, particularly in a writing class. That's probably a good idea because you're writing more stuff out. Okay? But remember, this is also now in the chemistry side of it. In the chemistry side, we know chemists are inherently lazy, which means we need to be using symbols. So we have to use the appropriate symbology to go through and solve this. So what do we need to be looking at? Atoms of, well, an atom of fluorine by definition is now F. Okay? In and of itself, that's not an inherently big issue until we read the rest of the question. What are we given?
2.25 grams of fluorine gas.
We're given grams of fluorine gas. Okay, but again, writing it out that way doesn't give us the symbology or the easiest way to cancel those units. So we need to use our shorthand notation for that. And what is our symbol for fluorine gas? F2. We should immediately be having an issue here. What do you notice as you go through and solve or attempt to look beginning to end?
It's the wrong units.
It is the wrong units. What part of the units are wrong? Both parts. I have a measurement unit of grams to a measurement unit of atoms. Okay? They are technically both measurements, but the measurement unit has changed. F2 is a substance, F is the new substance. Are the substances the same? No. So we're going to have to convert at some point both the measurement and the substance. Okay? Those two things should never be converted at the same time. Okay? It is theoretically possible to do it, but what you have done is combined two independent conversion factors, and that's where things can get wonky on you, because you have to memorize that process. Okay, so what should we do?
Over one.
Okay. This one becomes a bit tricky. Grams is not the same thing as atoms. F2 is not the same thing as F. Okay, so nothing matches. How do we know where that grams of F2 should be? Should it show up in the numerator or the denominator? That's arguably a very difficult one to kind of assess. The easiest place is to start with it in the numerator, and the argument that I would use is that this is a single measurement, and this is a single measurement. If I put my starting measurement in the denominator, where would I expect my ending measurement to be? In the denominator. So because they're both single measurements, we'll keep them both in the numerator, because that's what the answer for sure is in the numerator. Okay? So what's our next step? Times
1 mole over 38 grams of fluorine gas.
Okay. So I'm going to complain with number one where you started. What did you start with?
1 mole.
1. 1 I'm already going to freak out at, because 1 is irrelevant without the unit. We need the unit to figure out what numbers we're supposed to be placing. Okay? You're reading off your work, and your work may be perfectly all right. Okay? And that's not I'm not trying to start that argument, but we need that process. Follow the unit.
Let me try again.
Okay.
So you're going to want to cancel out grams of fluorine gas.
Okay, so the idea is I don't want grams of fluorine gas, so I'm going to put that in the denominator so that it cancels. It looks like an 8. It's starting to bother me. Okay? What do I want to convert it to?
Maybe a mole.
Okay? We'll come to that in a second. Ideally, what do I convert it to?
Atoms of F.
Atoms of F. Can I do that conversion? Why not? It doesn't exist because it's a substance conversion and a measurement conversion. That is our reason for why that one doesn't exist. Sometimes they're more obvious than others. That's the most obvious wrong conversion factor you're going to find. We won't convert measurements and substances at the same time. Okay? So what do we want to convert grams of fluorine to? Or fluorine gas to? Okay. The suggestion was for moles of fluorine gas. Why moles of fluorine gas? Okay. I think I might have heard something mumbling about atoms. Okay. So what Molly is suggesting is that we want to go into moles of fluorine because I know to convert fluorine gas into fluorine, I could use the chemical formula. I could use a counting measurement for the chemical formula. What unit or measurement is my counting unit? Moles. So if I can make it into moles, I now have a counting unit that I can now convert fluorine molecules into fluorine atoms. Okay, which is going to get a bit weird there, but we can do it. What is that conversion factor?
2 atoms, 1 molecule.
There are 2 atoms in 1 molecule. How do you know that?
Because it's F2 and then F.
Everybody has a hard time with that. I'd have a hard time explaining that answer too, because that's what the formula says. That 2 means that there are 2 F's in that unit. That's all I got. Okay? So what you've acknowledged is that to change that substance, I have to be in a similar unit. Whoops. And we could have put that unit on there, which is moles. Okay? I have to be in that counting unit. So if I can get into moles, I can use this conversion factor. So what am I going to do? Convert to moles right out of the gate. Right? What is that conversion factor? Where is that conversion factor between mass and moles found? It's found in the periodic table, and the periodic table tells us the mass for F2 is 38 grams of F2 in 1 mole of F2. Okay? What happens with my units? Grams of F2 cancel. Moles of F2 cancel. What would I now have? Moles of fluorine atoms. What do I want for an answer? Atoms of fluorine. Am I there? What do I need to do? I need moles of atoms of F to become atoms of F. Where's that conversion factor found? Okay, this was a chemical, sorry, let's backtrack. That is found in your memory, tied to whose name? That looks horribly wrong to me. I think it's Avo. In any case, Avogadro's number, and what is Avogadro's number? Times 10 to the 23rd atoms. Is what? 1 mole. What happens? Moles. Whoops. No, I had that right. Moles of F cancel. Now I can punch it into the calculator. 2.25 times 2 times 6.022 times 10 to the 23rd divided by 38. And we now have our answer. Okay? What's the question? Or are there questions?
Me and Molly are confused.
Yeah, I don't understand why what is he missing there is because why do you have to multiply by 2 if you have the 38 down there already?
Why is the 38 here?
It's for F2.
This is for F2. Why is there a 2 here? It's for F being in F2. Are those numbers coming from different reasons? Yeah. Okay. This is where someone can make 2 mistakes and get the answer right. What are the 2 mistakes? Instead of writing 38, they would write 19, which is not the molar mass for F2. They can get away with that if they don't do the other 2 conversion. So you end up doing 2 conversion mistakes that negate each other, okay, because you've decided to internalize that conversion. Do not internalize conversions. It works well in simple circumstances. The instant it stops being simple, you start to internalize it and you get it wrong. Do not internalize conversion factors. Okay? The chemical formula is a different source of information than the periodic table. Okay? If anybody's curious about that and going, I don't believe you, find F2 on the periodic table. The instant you can find F2 on the periodic table, I've never actually bothered to check. It might show up somewhere in there. Okay? Then maybe we can have that conversation. Those are 2 different pieces of information. Do not bring them together. Okay? If you bring them together correctly, you then start setting up the situation where now you could get the right information. You got the right information for the entirely wrong reason. Okay? Which can be insanely dangerous. So you have to have the right reasoning behind it. Okay?
So do you think 2 over 1, is it largely equation-wise to get rid of the F2?
It's to get rid of the F2. Yep, it's to convert F2 into F. So we have the periodic table getting us information on converting grams, which is what kind of a measurement? What do grams measure? Mass to moles, which is a measurement of, I kind of understand units or things. I would say counting is what I've been using as my term. Okay, so mass to counting. What's the other one? What is the chemical formula giving us a unit conversion from? Substance to substance with what measurement? What are moles a measurement of? Counting. What are moles a measurement of? Counting. Okay? The periodic table gives me mass to counting. The chemical formula gives me counting to counting. Avogadro's number gives me counting to counting. It's still a counting to counting. Okay? Atoms is just a large count, so is moles. Okay? It's an invented unit so that we can scale to an appropriate mass. Okay? When it's a chemical formula, particularly the diatomics, it's really easy to combine the chemical formula conversion and the periodic table conversion. Okay? And some people do that internally. Okay? That only works for the diatomic elements. What if we switch it to a different compound? You wouldn't be able to combine it, and now you get the answer wrong because you don't know where to find those conversion factors. Okay? Separate each individual step of your conversion. Okay? Which gets us to the next fun one. What does a chemical equation allow us to do? If I give you chocolate chips, what could you do with chocolate chips?
Eat them.
You could eat them. You could turn them into cookies. How'd you turn them into cookies? You mix them with other things. Okay? You mix them with pineapples. Ew. Why are you saying ew? Chocolate chip cookies don't have pineapples in them? No. Well, how do I know they don't have pineapples in them? Because it doesn't say, what do you mean? What's it? What is it that doesn't say it? The baking equation. Way to use fancy words on. I would argue it's just a recipe. What is a chemical equation? A recipe. That's all it is. Okay? It allows us to convert one thing to another. What was the chemical formula? A recipe. A chemical formula allowed us to convert fluorine atoms into fluorine gas. What do chemical equations do? The exact same thing, but now with molecules. Right? So a chemical equation is going to give you that same substance conversion, which is going to be in units of counting. Okay? The example that we typically, or I typically like to use, is trying to build a bicycle. What are some simple instructions on how to build a bicycle? You've all seen a bicycle, right? How would you build a bicycle?
Tools, parts.
You would take two wheels and you attach it to a frame. Ta-da, bicycle. Simple instructions. Okay? Could I simplify those instructions more? No? I couldn't simplify those at all by, say, putting a 2 in front of the wheel? Oh, I guess I could. Yeah, we could simplify it a little bit. Okay? That's now a chemical formula. We can use that chemical formula to solve questions. Solve questions like someone built 4 bikes. How many wheels and frames were used?
Put some parentheses there and there.
Okay? The long pause makes me a little bit nervous because theoretically you would be able to do this in your head. It's okay if you can't. What is our process for doing this? I want to know how many wheels. What do I do? I start with 4 bikes. I need the unit of bikes to disappear, and what do I need? Wheels to up here. What is the relationship between bikes and wheels? It's 2 to 1? Oh, it is 2 to 1 that way. 2 wheels, 1 bike. Now what happens? I canceled out the units, and I get 4 times 2, 8 wheels. Good job. That's chemistry. Okay, that's chemistry at a macro level. We're used to it at the macro level. Why has it become so much more challenging when we move to the micro level? How many of you have seen a molecule? You haven't. Okay? Can we even react molecules? It's kind of challenging. You're like, don't we like mix molecules together and react? Do we react a single molecule with another single molecule? No. We can't measure that. What do? We mass them out. To mass them out, how many molecules are we looking at? Not even billions. 6.022 times 10 to the 23rd. Billion is just 10 to the 9th. I don't think it's 9. Is it 6? Or is it 9? It is 9? 10 to the 9. We still can't even measure a billion molecules on our balances. Okay? That's how large the amount of molecules is that we're measuring. Okay? And we're throwing all those molecules together and hoping that chemistry does its thing and they react. We aren't even discussing why they're reacting. We're just saying they do. Okay? A rough analogy is I take those two wheels and that frame, and I take a big bag, and I put the wheels in the frame into the bag, and I close the bag, and I just shake it a whole bunch, and I open up the bag, and there's my bicycle. That's what we're doing in chemistry. Okay? But chemistry or chemical molecules have certain properties associated with them that they will seek each other out when we put them in that magic bag. Okay? That's what we're trying to do. Okay? Given 6 wheels and 3 frames, how many bikes can be made? 3. Okay, you're running those calculations relatively quick. That's awesome. That's fantastic. You're used to dealing with those. Okay? Just 2 wheels, how many bikes can be made?
0.
0? Why 0? Okay? This is where reading the question very carefully comes into play. It says, given just 2 wheels, how many bikes can be made? The reason why I put this one on here is that we tend to phrase chemistry questions like that, where the answer we're fishing for is 1. Okay? So we have to be careful with the phrasing of our chemistry questions. I do try and phrase them appropriately so that we don't accidentally stumble into that, oh, well, if I only have 2 wheels, I can't make any bikes because I don't have any frames. Okay? So we do have to be careful with the English language.
So if we were given, if we came across that on an exam, what should we do?
You came across that on an exam. Here are your answer choices. One. Why not 0? It's not an answer choice. Okay? So that's a really unfortunate phrasing of question because the answer should be 0. Okay? Sometimes chemists do well at understanding the English language, sometimes they don't. Look at me. Okay? We need to make those adjustments and watch out for them. I do attempt to make sure that we don't encounter a vague question like this. How would you know that you need to watch out for it and assume that there's a bunch of frames? Look at your answer choices. Does the 0 answer choice show up? No, which probably means you should assume enough frames to build it. And you're only given those 2 wheels as kind of your limiting factor. Right? 3 wheels and 2 frames, how many bikes can be made? But with 2 frames, I can make 2 bikes. But I run out of wheels. Okay? A unicycle is not a bicycle. It doesn't count. Okay? Everybody goes to that. It's not enough. Okay? It's still not a bicycle. It's still not a tricycle. Okay. So we're doing those interpretations from that chemical formula. You are going to be expected to run questions exactly like these with a chemical equation. Right? That requires effort. Let's bring the last one in just to see, I think the last one in. 40 grams of wheels and 15 pounds of frames. How many bikes can be made? What do you mean you're not familiar with it? You answered every other question like spot on perfect. What the heck's wrong with you?
Yeah, because we're familiar with it. This one we don't have to actually do that.
What's the issue with the unit? We went from counting to mass. What does the chemical equation give us? Just counting. Can you use the chemical equation with mass? No. What would you have to do with the mass? Convert it to counting. You do the same thing with chemistry. You will have to convert mass amounts into a counting unit so that you can then do a counting to counting conversion with the substance. Right? So, how many moles of CO2 are necessary to make 1 mole of sodium hydrogen carbonate? You guys did this like lightning on the last slide. I don't know what's wrong with you. Oh, interesting. There's a little bit of decoding that has to come into this. Okay? Maybe that decoding has to do with the fact that you have no concept of what those symbols mean in the real world. Right? Because even if I'd gone back to this previous, this previous example, and it changed this whole thing, come on now. Instead of showing pictures, I'd written bike, frame, that says frame. Reference the writing comment made earlier. 2 wheels plus frame equals bike. You would still have been able to get through to now this language, or you all of a sudden be like, whoa, I can't do that anymore. Okay? You've put a false presumption on that it doesn't connect. It's the exact same theory. It's the exact same process. Okay? What are you solving for? What are you starting with? And in particular, what measurement unit of sodium hydrogen carbonate?
2.
What unit?
2.
What unit? 2 is a number. What unit? Mole. What number? 1. Okay. Now what do I need to do? Does the substance change? CO2 versus NaHCO3. Did the substance change?
Yes.
Yes, just a little bit, like most of the molecule changed. Okay? How do I convert substances? A conversion factor. A conversion factor found where?
In the
Kind of except above. What is that?
chemical equation.
A balanced chemical equation. It has to be balanced. If it's not balanced, it doesn't work. Okay? So, in that, I'm trying to get rid of the units of sodium hydrogen carbonate and ultimately the mole measurement. And I want the mole measurement of CO2. Where do I find that conversion factor? The chemical equation. Where in the chemical equation? Right there. There, we talked about there, I think, in the English class. You got to be a little bit better with theirs.
There is 1 mole of CO2 for 2.
How do you know 1 CO2?
Because there's no prefix.
The coefficient, the number in front of CO2, isn't specified. It's an implied 1, because if it was an implied 0, there wouldn't be CO2. Okay? So I could put 1 here. How many moles of sodium hydrogen carbonate are there? 2. What's my answer? A half a mole of CO2. Can I have a half of a CO2?
Half a mole of CO2.
Why? Didn't I just say that?
You said half a CO2.
What's the difference between a half a CO2 and a half a mole of CO2?
A mole is counting. CO2 is
They're both counting. I cannot have a half a CO2. I can't do it. But a half a mole, you're saying I can. Why can I have half a mole of CO2?
Because you're not cutting CO2 in half, you're cutting the number of CO2 in half.
Better, but if my number is 1, I'm still cutting the number 1 in half.
2, 2, 3,
Okay, if we can't divide eggs, we can't break up eggs, can I have half an egg?
No, you can have that.
No, because I can't have half of an egg. I said I'm not allowed to do it. Could I still have half a dozen eggs? Yes. Why am I allowed half a mole? What is a mole? A very large number of molecules. I can have half of a large number. That's allowed. I can't have half of a single molecule. Right? That's one of the powers of a mole. That now allows me to get into fractional values that is useful. Right? That's the beauty of the chemical equation. I can convert those substances. Okay? We're going to skip that for the moment and that. So, what we've got is a chemical equation. The chemical equation gives us a counting effect. Mole is probably the most, or arguably the most useful count within it. But are there other counting units? Well, yeah, a molecule works as a counting unit. Right? 2 molecules of nitrogen oxide will react with 1 molecule of oxygen to produce 2 molecules of NO2. Right? So what happens if I now go to 1,000 molecules of oxygen? How do I know that it's 2,000 molecules of nitrogen oxide and 2,000 molecules of nitrogen dioxide? Okay. We're recognizing the chemical equation establishes a conversion factor, a ratio that allows us to convert. When we scaled up, we just multiplied by 1,000, which means for the other ones, what do we have to do? Multiply by 1,000. Okay? Did I have to do just 1,000 molecules? No, I could have actually picked 6.022 times 10 to the 23rd molecules. How did I move from 1 molecule to 6.022 times 10 to the 23rd? I multiplied 1 by 6.022 times 10 to the 23rd. How many molecules of nitrogen oxide would I have? 2 times 6.022 times 10 to the 23rd, which is 12.04 times 10 to the 23rd. Okay? Do I have to use that amount of molecules? Could I use 2 molecules?
For what?
Good qualifier. For what? For going into lab, can I use 2 molecules?
No.
Why not?
Too little amounts.
They're too small, I can't measure them. Could I use 2,000 molecules? Nope. That's also way too small. I have to measure out 12.04 times 10 to the 23rd molecules. Okay? How many of you like powers of 10? Oh, okay. So we want to invent a unit so that the power of 10 stuff disappears from this. Okay? That unit I'm going to invent is moles. What happens? 1 mole. The other one becomes 2 moles. Last one, 2 moles. In each of these cases, what we are doing is creating a conversion factor. Okay, and the last one is wrong. 2. It's all right to figure out what it was. Okay, in this chemical equation with 3 different species, okay, I get a relationship. 1N2 equals 2NO. 1O2 equals 2NO. 1N2 equals 1O2. There were 3 equalities there. Each of those equalities generates 2 fractional equations, which means this single equation gets me 6 different conversion factors. Okay? Getting back to the whole memorization part, okay, well, I just want to memorize something. Every equation generates probably at a minimum 6 different conversion factors. Considering there's an infinite amount of equations, you would have to memorize an infinite amount of conversion factors. Or you learn to interpret what the equation means. You have to be able to decode that information. That's the beauty of the equation. That's what allows us to learn and move forward. Okay? We will look at that equation, but the one I want to get at before we leave, this one. This should look really familiar. This looks roughly like what was on your exam. Okay? And everybody flips out and freaks out at it. Literally everything that you need to solve the question is in the question. All you have to do is follow the process that we've talked about for 4 weeks. Okay? Admittedly, when you first saw it, it was only 2 weeks of talking about it. Okay? We've now had 4 weeks of talking about it. Follow that process. You follow that process, you get the correct answer. This next unit, though, becomes more difficult because most of that information you already had on the exam. You just didn't know where it was. So the question becomes this. 9 grams of oxygen gas are reacted with excess hydrogen gas, then how many grams of water are produced? You're still expected to be able to get the exact same answer. You have all of the tools to be able to answer that question. We'll look at it again on Tuesday.